Good evening, good morning, wherever we're at. So what we have here is we have efficiency and entropy. We already covered entropy, so I'm going to go ahead and go back past those slides till we get to efficiency, and we will start off right here. So what we're going to do today is we're going to kind of explore the efficiency of heat engines, and we'll start off with the White Cliffs heat engine right here, which is a solar array that's in Australia. Now, it did work. I can't remember what year it stopped working, but they were off the grid. They were pretty far out there, isolated, and so they needed to get some electricity where they weren't being able to plug it into the, Australian gas and electric. So the sunlight shines really good out there in Australia, right? And so they use this solar energy to focus sun into an area that would actually boil water. And so there's going to be this energy is going to be focused in, it will boil water, and the boiling, the heat can go through our pipes and it can go into a steam engine, which is on the inside of the building. And so here's the steam engine. The steam would come into the top through the pipes. That would cause, let me change the color here so you can see it better. That would cause, I like this color over here. And so that would cause the internal energy to be raised, which would cause these to be able to push up and pull up, and that would do useful work on this shaft right here. And so this shaft is connected. This shaft will be connected to an electrical generator. And so you're going to convert sunlight energy to steam and steam energy into kinetic energy of rotation, and then that rotation will turn into generating electricity. So that's a very awesome machine, but let's find out about how we would calculate how efficient is something. So one of the things I want to do is I want to start off by saying, how efficient are you on an exam? So how do you figure that out? It's actually pretty easy. You do this all the time, I'm quite sure. You take your score that you got, and it's over the score that you could have got. So it's points possible minus points not earned over points possible. So 65 was what I could have earned. 10, no, I'm sorry, I didn't get those, over 65. So that's 55 over 65, which is literally what's always written on your exam. And that gives you, if you do the division, you get 0.846. You times that by 100 to change that to a percent, 84.6%. Yay, not too bad. Not an A, but not too bad. So how does that apply? It's the same exact idea of how you would apply that to a solar engine. So we could go back, and we're going to do this one actually, but we're not going to do that one first. Let's do an easier one first. Let's do our Stirling engine from class. So here, this isn't the Stirling engine. This is just a beginning example here. So let me go ahead and take a look at the overall equation of what's going on. So QH is this. It's the high side of the heat. It's the hot side. But it always has to deal with the low side on the outside. The ambient temperature is causing back pressure, and so the amount of work that you can do is always a difference between the hot side and the cold side. So instead of using heat, which is joules, we're going to use temperature, because temperature is related to the amount of heat. So the more heat you got, the higher the temperature usually. And so we're going to use temperature in kelvins. And so the energy possible on this side will be our high heat side, our high temperature side, and the ambient temperature of the room will be our TC, which is our cold side of our temperature. And that difference is what we're going to use in order to find what's called ideal efficiency, which is the best we could possibly do under this circumstances. So let's take a real example then, and let's see if we can talk about our Stirling engine in class, which we actually did, or I actually did. What was the high side? So the high side was hot water, and that hot water was about 60 degrees Celsius, but we can't use Celsius. In order to get from Celsius to kelvins, we have to do this. Kelvins is equal to our Celsius plus 273. So 60 plus 273 gives me 333 kelvins, and I put that right there. That's my hot side. And my cold side was room temperature. It was 22 degrees Celsius, it was a little colder than the 25 you'll see on the wall of my poster. So add 273, I get 295 kelvins. And so here's my 295. So The best I could have done with that Stirling heat engine was 333 minus 295 gives me 38, and 38 out of 333. That's the best I could have possibly done that day. That is 11.4 is my ideal efficiency. So right out the bat, how could I make this 100% efficiency? Well, number one, it's impossible, and I'll tell you a couple reasons why. We'll start off with this one. So how do I make it 100% efficiency? What does that number got to be? That number has to be zero. What the heck is 0 kelvins? That's absolute zero. And so maybe you can think about this. Maybe you already got that in your head, but absolute zero is an impossibility. You will never get there on Earth. You won't get there on Mars. You likely won't ever get there in space. We've never even really measured absolute zero because all of our measuring devices for measuring temperature require energy. And so the moment you bring that measuring device into the area, which would potentially be absolute zero, you destroy absolute zero because you bring energy there. We've gotten pretty close, like within decimals, but we haven't actually gotten to a place where we can say it's definitively absolute zero. I guess the deep recesses, the vacuum of space might be absolute zero, maybe, I don't know, but we've never gotten there. So it's impossible to get 100% efficiency. It's impossible to get 100% efficiency because we can't get to absolute zero. The outside temperature, this outside temperature is never going to be, the ambient temperature outside is never going to be absolute zero. 11.4 ain't great, but it's not super horrible either. So, that might be the same as a typical Buick or something like that. But so this is a typical type of ideal efficiency, actually. But ideal efficiency is not actually saying what your actual efficiency is. Well, what the heck are you talking about, Mr. Morrison? I'll show you on the next page how you would get actual efficiency compared to ideal efficiency. So the way we're going to do this is we're going to look at an actual working steam engine. And so this one is absolutely positively a working steam engine. This is the one we were talking about before, which is the White Cliffs. This is solar steam generator, and this is in Australia. And this is comparing ideal efficiency with actual efficiency. Okay? So the actual efficiency was measured by the company. This is a energy company. So I will talk about the actual efficiency in a moment, but let's talk about ideal efficiency first since we're on that idea. Okay, so here's my table, which I'm kind of exploring these temperatures, right? So the temperature we're going to look at is this one right there. That's that point we're going to look at right there. That's at 220 degrees Celsius. So I can't use Celsius, remember, I got to use Kelvin. So let's convert that. So 220 degrees Celsius is going to give me 493 kelvins. Here's my calculations, TH minus TC over TH. And so there's my 493 over 493. Okay, what is the ambient temperature? Well, I'm just going to say the room temperature is 25 degrees Celsius, which is the one that's pretty much on the poster on our wall in class, so that's fine. So this is my low temperature. This is my TH, because I read it off the graph. That's the point right there. And this is the TC, which is basically almost always going to be just whatever the ambient temperature is. So I put 493 minus 298, and then I divide that by 493, and I get 39.6, that's a lot better than our little Stirling engine, right? But how does that compare to our actual efficiency? So over here is the company is wondering how efficient their machine is. And so this graph was showing us actual efficiency versus steam temperature. So right here, this is your actual efficiency as measured by the company. So they can measure how much work was actually put out. And so they can tell you the actual efficiency. We can't really tell you from what they've given us that. So look at that. 12% actual efficiency. The actual efficiency was 12% as shown on the graph. So what the heck is going on? Well, first of all, we know this number is not going to be 100%. And it's not going to be 100% because the ambient temperature is not even anywhere near zero, right? It's not anywhere near zero. There's a second reason. Do you remember that our steam engine in class? Do you remember like they had pipes, right? And you could actually see the steam kind of coming out of the pipes a little bit, right? And you probably could feel heat coming off. If you put your hands near the pipes and hands near the heat is escaping. So not all of this 493 kelvins. Not all of it actually, the potential is actually being used to do work. It can't. It's escaping. And so right here it says ideal efficiency is always greater than actual efficiency. That's an obvious. And it's due to heat loss, which is called thermal pollution, and friction. If you get rid of all thermal pollution, all heat loss, that would mean that every single joule of heat that you produced would go into work. Then you take it so that every single joule is turned into work, and then you eliminate the ambient temperature down to 0, and then you will get 100% efficiency. But as I said, that's not going to happen. 3 reasons: because you're losing heat, you're battling friction, and you can't work in an environment that's absolute 0. Okay, so that kind of leads us to the next item, which is going to be our summary. And so here's our little summary. It says efficiency. Why is the actual efficiency, I don't know if I'm sure if I'm going to get my drawing tool back here, but why is the actual efficiency always lower than ideal efficiency? Ideal efficiency, this is our equation. It's the hot side minus the cold side divided by hot side times 100 will give you your ideal efficiency. 100% efficiency is not possible for 2 reasons. It is impossible to have a sink of absolute 0, right? You can't just go into absolute zeroness. I mean, your car would literally have to feel like it was absolute 0. Then you would know all that heat energy went into work. And it's impossible to lose 0 heat due to friction, etc. Did you see the in-class steam engine leaking steam out of the pipes? I don't know about you, but I did. Did you see Mr. Morrison add oil to the piston to make it run smoothly? I don't think I did that for both periods. But there's oil there, and it runs kind of loudly, and I put a little oil on it, and then it gets quieter, right? So that's the idea. Let's see if we can't use these ideas and do the quiz now with those numbers in mind. So let's go ahead and go back a slide or two, because this is the one that's difficult, to make sure you got what's going on. This table of temperature just makes sure that you understand what's going on with kelvins and degrees Celsius. These are the only 2 that are really in use on this graph. I was just trying to make sure that you understood that if water boils at 100, which would have been this would have been the temperature of our in-class steam engine, right? When we did the little steam engine in class, I did not get that thing. I did not get that thing up to 220. That's actually really stinking hot. The other thing you want to look at is this little note here, right? What's happening to efficiency as you get hotter? What is happening to efficiency as you get hotter? And hopefully you can see the answer is as you get hotter, higher temperatures equal greater efficiency. And one of the reasons that is because the lower temperature is staying the same. So as you increase this, then your efficiency will also increase, but to a point. You get too hot, the thing is going to blow up. So you got to be careful with that, right? So it does kind of rise, and then it kind of flattens out at the end. So maybe this machine is getting to the point where it's going like, hey, don't go any hotter. So anyways, let's go ahead and see if we can use these things to answer the quiz questions.